Hello everyone, welcome to another lecture of the course Digital Signal Processing. In the previous lectures, we have seen how to design a causal FIR filter. So in this lecture, let us consider a simple example for the same. So let us consider the situation in which we need to design a low pass FIR filter with the specifications as the passband edge, that is FP, is given as 1.5 kHz. The transition width is required to be 0.5 kHz. The sampling frequency is given as Fs equal to 10 kHz and the minimum allowable stop band attenuation is 50 dB. So using these specifications, let us start designing the filter. Now if we observe these specifications, that is passband edge, transition width, sampling frequency, we can see that this is all for the continuous time signal, but we need to design a discrete time filter with a sampling frequency as 10 kHz. So first step is to convert these continuous time parameters to discrete time parameters. So the first step, the step 1 is to map continuous time parameters to the discrete time parameters. So map the continuous time parameters to discrete time parameters. And this can be done by using the formula as omega is equal to 2 pi f by fs. Now if we observe here, what we need to find is the passband edge in the omega. So the passband edge in the discrete time frequency, that is omega p, can be calculated as 2 pi fp by fs. That is equal to 2 pi into fp, that is 1.5 kHz. So 1.5 into 10 raised to 3 divided by the sampling frequency, which is 10 kHz. So if we simplify this, the omega p value is obtained as 0.3 pi. One more parameter that we can find in this omega domain is this transition width, that is delta f. So what we can find is delta omega, which is equal to 2 pi delta f by fs. So this delta f is given as 0.5 kHz. So 0.5 into 10 raised to 3 divided by 10 into 10 raised to 3, which is equal to 0.1 pi. Now in order to find the cutoff frequency, we need to find the stop band edge also. So if we remember the typical frequency response for a low pass filter, it was something like this. So this was the passband edge, then a transition width, and then stop band edge. So this part or this frequency was the passband edge and this frequency was the stop band edge, and the region, that is the difference between this passband edge and stop band edge, was the transition width, that is delta omega. So this delta omega can be represented as omega s minus omega p, where this omega s is the stop band edge, and therefore it can be calculated as omega s equal to delta omega plus omega p, which is given as this 0.3 plus 0.1, that is equal to 0.4 pi. So now we have the transition width, the passband edge and the stop band edge in the omega domain. So using this passband edge and stop band edge, we can find the cutoff frequency. So the next step, that is step 2, So the step 2 is to find the cutoff frequency. And this cutoff frequency is simply the mean of the passband edge and the stopband edge. So this cutoff frequency omega c can be calculated as the mean, the arithmetic mean of the passband edge and the stopband edge, that is omega p plus omega s divided by 2. So if we look at the values, the passband edge is 0.3 pi and the stopband edge is 0.4 pi. So what we have is 0.3 pi plus 0.4 pi divided by 2, which is equal to 0.7 pi by 2, that is equal to 0.35 pi. So the cutoff frequency value we obtain as 0.35 pi. So this is the cutoff frequency. So the filter that we need to design has the cutoff frequency as 0.35 pi. Now we have the cutoff frequency and we need to design a FIR filter. So in that case we need to find what kind of window do we need to take. So this next step, that is step 3, is to determine the type of window, and this is to be determined using the specifications that we are given. So depending on the specifications, we need to determine the window type. So determine window type. So the specifications that we have is passband edge, transition width and sampling frequency, and also the minimum stopband attenuation, which is given as 50 dB. So using this specification we can very well determine the window that we need to take. So let us look at the table of the parameters for a window. So these are the specifications for different types of windows, and if we observe this Hamming window, it has a stopband attenuation of minus 53 dB. And if we observe this rectangular window, Bartlett window and Hanning window, all these windows have stopband attenuation less than 50 dB, but this Hamming window and Blackman window have the attenuation that is higher than 50 dB, and we had been given that the minimum attenuation should be 50 dB. So we have two options, that is Hamming and Blackman window. But now if we look at the transition width, that is for Hamming it's 8 pi by m and for Blackman it's 12 pi by m. So we can very well see that this Hamming window has a lower transition width. So let's prefer this Hamming window for our design. So what we are going to do is we are going to take the Hamming window depending on the specification of minimum stopband attenuation. Now we have chosen the window, we know the cutoff frequency. One more specification that we require to design a filter is the order of the filter. So the next step, that is step 4. So the step 4 is calculation of order, that is M, for the filter. And for finding the order we are going to use this formula, that is the transition width for the Hamming window. So the transition width, that is delta omega, for Hamming window is given as 8 pi by m, and in our case This transition width we have found as 0.1 pi. So let us substitute it here. So this 8 pi by m is equal to 0.1 pi. Therefore the order m can be calculated as 8 pi upon 0.1 pi, which is given as 80. So the order of the filter is 80. So now we need to design a low pass FIR filter with cutoff frequency as 0.35 pi and order 80, and the window that we are going to consider is the Hamming window. So after this, the next step is to determine the equation or the expression for the ideal low pass filter. So the step 5 is find expression for ideal filter, that is H ideal of n. And we are going to design a causal filter, so we need to consider this expression for the shifted version. Therefore the shifted version can be found as H ideal of n is equal to sine of omega c into n minus m by 2 divided by pi into n minus m by 2, and this is valid for n not equal to m by 2, and which is equal to omega c upon pi, and this value is for n equal to m by 2. Therefore for omega c equal to 0.35 pi and m equal to 80, the expression for the ideal filter, that is H ideal of n, is equal to sine of omega c, that is 0.35 pi, so omega c 0.35 pi into n minus m by 2, so m is 80, therefore 80 by 2 is 40, divided by n into pi into n minus m by 2, so this is again n minus 40, and this is valid for n not equal to m by 2, that is n not equal to 80 by 2, that is 40. And for n equal to m by 2, that is equal to 40, it's omega c upon pi, so this omega c is 0.35 pi upon pi, so this is equal to 0.35. So this is the expression that we obtain for the ideal filter for the cutoff frequency as 0.35 pi and order as 40. Now as we have the expression for this ideal filter, we also need the expression for the window. Therefore the next step, that is step 6, is to find the expression for the window, that is W of n. And for this example, we have obtained the window as the Hamming window. And if we look at the expression for the Hamming window, we can see that for the causal filters, that is n ranging from 0 to m, the Hamming window expression is given as W of n equal to 0.54 minus 0.46 cos of 2 pi n upon m. So let's use this expression to find the expression of W of n. So W of n for Hamming window is 0.54 minus 0.46 cos of 2 pi n upon m, and we have this m equal to 80, so W of n is equal to 0.54 minus 0.46 cos of 2 pi n upon m, that is 80. Therefore, the expression of my window is W of n is equal to 0.54 minus 0.46 cos of pi n upon 40. So this is the expression for the window. Now we have the expression for the ideal filter as well as the window. So the next and the final step is to determine the h of n, that is the filter. So the step 7 is to find h of n. And this h of n can be found by simply multiplying the ideal filter, that is h ideal of n, into W of n. Now this h ideal of n we had found as, so this h ideal of n is equal to, we had found it as sine of 0.35 pi into n minus 40 divided by pi into n minus 40 for n not equal to 40, and it was equal to 0.35 for n equal to 40. Therefore, this h ideal of n was sine of 0.35 pi into n minus 40 divided by pi times n minus 40, and this is valid for n not equal to 40, and it was equal to 0.35 for n equal to 40. And this W of n was obtained as W of n is equal to 0.54 minus 0.46 cos of pi n upon 40. So this W of n is equal to 0.54 minus 0.46 into cos of n pi by 40. And when we multiply this ideal filter and this W of n, we get this h of n, and the range and the values of n for which this h of n is finite is from 0 to m, that is 0 to 80. So for a length of 81, that is L equal to 81, we find this h of n. So by substituting n equal to 0 to 80, we can very well find the coefficients, that is the filter coefficients of this h of n. So in this lecture, we have seen how to design a FIR filter using the given specifications. So in general, the specifications are mostly mentioned for the frequency domain for the continuous time signals. So the first step is to map these continuous time parameters to the discrete time parameters. And once we do this, what we have is the passband edge, the transition width, as well as the stopband edge in the omega domain, that is for the discrete time frequency. So once we have this passband edge and stopband edge, so using this we can very well find the cutoff frequency, which is nothing but the mean, the arithmetic mean of passband edge and stopband edge. So if we have this cutoff frequency and we need to design an FIR filter, so we need to know what kind of window we need to choose. So depending on the given specifications like stopband attenuation, we can very well determine the type of window, and once we determine the type of window using the transition width formula, we can calculate the order of the filter. So after this step, we have the order, we have the cutoff frequency, and using these two things we can very well design the FIR filter. But for that, first of all, we need to find the expression for the ideal filter, which can be calculated as sine of omega c into n minus m by 2 upon pi into n minus m by 2, and this is valid for n not equal to m by 2, and it is equal to omega c by pi for n equal to m by 2. So after substituting all these values, we can find the expression for H ideal, that is ideal filter for given omega c, that is cutoff frequency and order. And after that, what we need to find is the expression for the window function, that is W of n. So for this example, we had chosen the window as Hamming window, and for that we had substituted the order value as 80, and using this we find the expression for the window. So once we have the expression for ideal filter and window function, we can very well find the filter, that is H of n, by simply multiplying the ideal filter and the window expression. And after multiplication of this, the valid range for n is from 0 to m, that is 80, where this 80 is the order of the filter. So in this lecture, we have seen the stepwise procedure for designing an FIR low pass filter. So let's stop here. Thank you.